Kinsyn III. In this film, a designer and a computer converse freely. Not only in words, they draw pictures for each other. Kinsyn III is a unique computer program for the design of linkage mechanisms. Linkages are used in many and varied situations to move objects, as in this street sweeper dumping mechanism. To trace out paths, as in this industrial sewing machine making shirt cuffs. Or to generate functional relationships between parts, as in this automated printing press. The design of mechanisms can be thought of as a process of invention. Kinsyn is a co-inventor of mechanisms. Kinematic synthesis is the design of a mechanism to meet preconceived requirements, and this is the main purpose of the Kinsyn computer program, namely the creation of mechanisms. Incorporated into the Kinsyn III system are capabilities for mechanism design, mechanism analysis, and graphic part description. Linkages may be designed to generate specified functional relationships between parts, specified paths, or preconceived motions of parts. How can Kinsyn be used to create mechanisms? One way is to simply lay them out freehand, using Kinsyn as a quick and easy draftsman. Another method is to tell the computer precisely what motion is required. Closed-form synthesis procedures find exact solutions to these problems. When exact solutions theoretically do not exist, Kinsyn's numerical synthesis finds optimum, though approximate, solutions. A proposed mechanism design can be immediately analyzed. Kinsyn transforms the design into a kind of erector set version, which is animated on the display. Finally, in addition to its schematic graphics capabilities, Kinsyn may be used to draw and manipulate actual shapes of machine parts. To show you Kinsyn in action, here are Dr. Roger E. Kaufman and his research assistant Andrew J. Rubel, developers of the Kinsyn system.
Up here on the display, we have a schematic representation of a linkage mechanism. This might be a clamping mechanism driven by link work. As you see, this link is toggling and it squeezes this pipe. It's actually a 6-bar linkage mechanism. As the drive continually rotates, it pulls up out of the way. An operator could reach in, pull out that part, then this mechanism would close down and squeeze the pipe again. Now this linkage was designed in about 15 minutes using the Kinsyn computer program that we're about to show you. The linkage was designed not by a trial and error process, but by a closed-form mathematical synthesis procedure. In other words, we started out by specifying the motion of that moving body, and the computer told us where these pivot locations and where these links needed to be in order to give us exactly that desired motion. We actually drew in these parts and then synthesized this mechanism to give us exactly these results.
in general, this type of design is very hard to do. What we are trying to do with this system is use the best aspects, the computational aspects of the computer with the insight of the human who can interact with the computer via this pen to get the best of both worlds and do some very, very difficult types of design which are not very easily done any other way.
The problem is really too difficult to simply delegate to a computer. A human being really needs to make creative and subjective judgments based on interacting with the computer in order to get realistic and reasonable designs. Now in my hand I have a pen, a ballpoint pen, which has a little switch in the tip, and there's a data tablet, a surface on which I can run this pen. The computer can sense exactly where the pen is on this tablet. Up on the screen, you'll notice that there's a little tracking cross, an X, which shows exactly where the pen is on the tablet. As I move the pen forward and backward on the tablet, the tracking cross moves up and down on the screen. As I move left and right, the cross moves left and right. When I press down with the pen, I grab an item off of this menu. Whichever item is closest to that pen hops onto the tip of the pen when I press the pen down. Now you see a directed line segment, the symbolic representation which stands for a moving body which is to be guided through some desired motion. On the display screen, the computer is showing the coordinates of the pen at any moment. So I can put this line segment down on the screen wherever I would like, and I can rotate it around by moving my pen on the data tablet. If I throw away with the pen and lift up the pen, the item jumps back onto this menu on the side of the screen.
You'll notice there's also a second tracking cross. We called it the image cross. This second cross is always located on whatever item is nearest to the pen location. In this way, to indicate or select some item, you merely need to go nearby, press the pen, and you can grab hold of one.
Each of these items on this menu is a schematic representation for a part of a linkage. This represents a hinge joint. This represents a fixed hinge. This line between the fixed hinge and the moving hinge really represents a link pinned to the framework at this end and pinned to a moving body at the other end. These other symbols represent sliders of different types. This is a pivoted slider. I can grab what we call the turning handle and I can rotate that pivoted slider around. This represents a slider with a straight slide track on the frame and a pivot holding it to a moving body. This top symbol, which I have now, represents a body to be guided through some desired motion. In other words, this is really like a coordinate system drawn on a moving body. You can consider the moving body as being infinite in extent, and this is just a directed line segment that is drawn on that body. We can use that to specify the motion of the body. I picked up another body. This really represents the very same body in an alternate position. Here it's numbered number 1 position, there's the number 2 position. You can see that it's shown dotted in the alternate position, and it's shown solid in the first position. If I grab more of these bodies, they all are really one and the same body, which we are trying to guide through these positions that I've specified. They're shown dotted in the alternate positions and solid in the first position.
Before synthesizing a mechanism for some required positions, why don't we try just building some mechanisms first without any requirements and seeing how they act.
Over on the right side of the screen, you see there's a button called Options. If I press the Options button, then brings forth a menu of many possibilities which are available from this synthesis part of the program. One of these options is to bring us to the layout mechanism part of the program, which allows us to create any kind of a linkage that we'd like, made with pin joints and sliding joints. The left side of the screen again, you see all of these different types of joints, which I can grab with my pen, or I can throw away by lifting up the pen. We can just simply build a linkage in this part of the program. Each part of the program has many, many options, which are part of the program. We won't have time to cover them all, but we'll try and cover some of the more basic options. I'm putting out some links and some joints and creating a 4-bar linkage. If I go over to this arrow and fasten that arrow onto that link, it means that that link is to be the driving link. I can now press the options button at the right of the screen and press the analysis button and see how that 4-bar linkage moves on the display. I didn't synthesize this linkage, I simply put it together. This is sort of akin to what a draftsman or a designer would normally do when building a mechanism, except that I did it much more easily. Normally a person might use cardboards and thumbtacks to build a mechanism, and making changes is a fairly time-consuming task. With the computer, it's very easy to experiment with different changes. Now here you see the schematic representation of this 4-bar linkage. There are the 2 fixed pivots, and there are 2 moving pivots.
And we control the speed of the driver or input to this mechanism through these data switches. So we can stop it, go forwards, backwards, show it in successive positions, and all sorts of other options which we'll be looking at. Why don't we build some more complicated mechanisms to see what we can come up with? Maybe we can add some parts to this 4-bar.
I'm putting an extra tracing point on the top of that. Let me put one of these sliders down there and hook that up to that tracing point. Let's see how that mechanism moves. The computer never needs to have seen any of these mechanisms before. On the fly, while we are doing this, the computer looked at the mechanism which I just sketched on the screen, and it derived closed-form procedures for animating and analyzing this mechanism on the screen. You can see that some of these are very pretty when they move around. This slider is going back and forth as that 4-bar is driving it through this connecting rod. Now that's a computerized way of doing what a draftsman normally might do in designing a mechanism. But what we have is a much more powerful capability than that. With this program, I can say to the computer, here is the first position through which I want to guide this body. It's shown solid up here. And then I put down a second body, and it's shown dotted. That represents the same moving body in an alternate position. And I want to guide it from this position down to this position. I want to know where can I put pivots so that a mechanism will guide the body through those given positions. I just grabbed a moving pivot, and the computer is showing me not only the pivot in its first position, but also a second pivot in the second position. It's the same point of the moving body. You see that little circle that's shown solid on the screen in one position and dotted in the second position? That's the same point of the moving body as the body goes from the first to the second position. There's also a line shown which is the perpendicular bisector to those positions and represents the possible locations for fixed pivots compatible with that choice of a moving pivot. If I grab a fixed pivot, Suddenly more lines appear on the screen. As I move my pen, I am constrained to move my fixed pivot only along those possible choices of fixed pivots. So the computer is serving as a computerized aid and helping me in my design task. Suppose I put the moving pivot at that point and I try choosing a fixed pivot that's compatible with it. The computer only lets me put the fixed pivot down someplace on that bisector line. Conversely, whenever I move this pivot, again, it's constrained to a locus of possibilities determined by this first choice that I made. Now I'm taking another pivot and trying to decide where to locate it. Again, I can put it any place on the screen, and the computer shows me not only where it is in the first position, but also where it goes in its second or alternate design position. As I pick the second pivot, notice that the computer occasionally flashes a bright box around the outside of the screen. What that means is that I found a linkage that will indeed guide this body through those two given design positions. At the bottom of the screen it says this is a crank rocker linkage. It has the driver at the right of the screen and it drives through all the positions in order. Now this is only a two-position problem, but let's see how it actually moves. Notice that with the aid of the computer I've designed a mechanism in a few seconds, and it does move that body from the number 1 position over here to the number 2 position. Now many people think that it's easy to design mechanisms for 2 positions or 3 positions because the geometry is fairly simple. Even though the geometry is simple, there are a lot of problems that you run into in carrying out such a design. You'd be surprised how many mechanisms don't actually satisfy all of the necessary conditions for moving through the desired positions, even for a simple 2-position design. Let's go back to the synthesis part of the program and just explore the possibilities for such a design. Notice here it's lit up the screen brightly with this box around the outside to say that that is a good design. But notice as I move along this locus, that box goes out to indicate that this mechanism, even though it can be assembled in the different design positions, won't move through them without being guided in between the positions. As I play with this pivot location, notice the flashing messages at the bottom of the screen. One of the beauties of this Kinsyn computer program is that it allows you to rapidly come up with working mechanism designs where you might have a great deal of difficulty working by some other technique. Now, by moving my pen up into the left corner, I'm going to grab another plane position for a 3-position motion which I wish to synthesize. As I move my pen around, I can rotate that plane position, I can grab hold of it, and specify any sort of motion that I might desire. Let's set it down over here. Suppose that I wanted to have a mechanism to move this body from position number 1 over to this 3rd position and then on to that 2nd position. How could I design a mechanism to do that? Well, if I grab a moving pivot fastened to the moving body, notice that the computer is showing me not only where that pivot goes to in the 2nd and the 3rd positions of the body, but it also is showing me where the fixed pivot needs to lie to be compatible with that choice of a moving pivot. In other words, that moving pivot is fastened to that body in the number 1 design position, and this is the only possible place where that fixed pivot can be and still have that choice of a moving pivot. If I grab the fixed pivot, the moving pivot needs to fall in a specific location for any given choice of the fixed pivot. The computer is showing me exactly where that location needs to be.
In the two-position design, we had a lot more design freedom. After choosing a moving pivot, we had a whole line, a locus, a singly infinite locus, to put the fixed pivot on. Now, as the number of positions go up, the constraints are greater, and so the computer is telling us that we no longer have as much choice. For one choice of a moving pivot, there's only one choice of a fixed pivot. So it only lets us put joints where those joints will satisfy these three design positions.
Now I have picked up a second moving pivot, and notice as I move it across the screen, as fast as I move my pen on the tablet, that pivot follows my pen, and flashing messages at the bottom of the screen tell me exactly what kind of 4-bar linkage I'm looking at any given instant. Right at the moment, it's a non-Grashof double rocker mechanism, and with either link as the driver, it would go through all the positions, but rocking back and forth. As fast as I move my pen around on this tablet, the messages keep flashing over and telling me exactly what kind of linkage I'm looking at on the screen. Here's a crank rocker, driver at left, misses positions 2 and 3. In other words, even though you could assemble this linkage in all 3 positions, it wouldn't move continuously through the positions.
When we're designing a 4-bar, as we are in this case, each of the 2 links which we'll be designing can either rotate continuously or be constrained to only rock back and forth due to the geometry of the mechanism. So that's what these messages are telling us, at least the first line. Each of the 2 links is either a crank, which can rotate continuously, or a rocker, which can only rock. Hence the terms double crank, double rocker, or crank rocker.
Now you see that it has lit up this box around the screen saying that this particular mechanism, which happens to be a double crank, does indeed go through all 3 positions in the right sequence. It makes it very easy for a designer to pick out a design that is compatible with his space requirements, because he just needs to concentrate on the space that the linkage is going to occupy, and when through the corner of his eye he sees that box suddenly flash on the screen, he knows that he's got a good working linkage. You can see that even for a 3-position design, again, there are many places where the linkage is not acceptable because it's not the right kind of mechanism or wouldn't fit the space requirements. And there are only little pockets where you can find good working mechanisms. Like right here, I saw a crank rocker that goes through all the positions in order, and the computer immediately called it to my attention by flashing that signal box. Here's a double crank mechanism that goes through the positions in order. In other words, we just saw probably 500 designs flash by in front of our eyes in a few seconds, and we're able to quickly evaluate them and pick out the one that best matches our requirements.
Now we can watch this mechanism actually moving, being driven, and it will move exactly through these 3 positions. The synthesis process that we just went through is a closed-form mathematical synthesis. So this is an exact solution. It goes precisely through these 3 positions.
We can speed the mechanism up or run it backwards or forwards. We can even make certain parts of the mechanism invisible so that we can study its performance better. We can make these coupler links invisible. And now that body, remember, is fastened to this coupler link of the mechanism, and it moves along with it. But just to clear up the picture a little, I selectively made those parts of the mechanism invisible.
We can have the computer stop erasing the screen every time it redraws it in the animation. So now we can watch the body go through its motion.
You can see that it does go exactly through those given design positions. Let's go back to the synthesis part of the program and try and design another type of mechanism for the same problem. Basically, a person can use this program with about 10 minutes instruction. He doesn't need to understand any of the theory for designing the mechanism. He simply needs to know that when he presses down with his pen, he can grab whichever item is on the screen that's closest to the pen. Now I grab the slider, and you see these 3 circles which suddenly appeared on the screen. They represent the loci of possible sliders for these 3 given design positions. And now I'm specifying a direction of sliding, and you can see that for any given desired direction of sliding, the computer is showing me exactly where the slider needs to lie. So suppose I wanted to design a double slider mechanism. If it's possible to do something, Kinsyn allows you to do it. I just grabbed the second slider, and let's see whether that satisfies the requirements. Here's a double slider mechanism. If a designer naively tries to do something that is impossible, Kinsyn immediately tells him that it's impossible, and this is one of the beauties of this program, that immediately allows you to weed out unfeasible designs and settle in on a feasible design. See, here are 2 sliders sliding back and forth, and they are causing that body to go through exactly those same preconceived positions which I put out on the screen. Here's a pivoted slider. Suppose I grabbed it. This circle represents the locus of pivoted sliders, what we call turning blocks or concurrency points. So let's try and design a turning block mechanism to move through these same 3 positions. With Kinsyn, there's one. With Kinsyn, we don't need to have a preconception of the kind of mechanism that we're going to use. We can simply try out different ideas, and if it's possible to design a mechanism of that type to satisfy those specific requirements that we've asked for, the computer will allow us to do it. So here's a totally different kind of mechanism with a pivoted slide block, and you can see that it goes through exactly those same positions, but in between the design positions it does it in a very different fashion. Maybe we could run it a little faster, Andy. Goes over into the first position, down into the next one, and then it scoops up and lifts up and dumps over and goes back. Maybe we could make this into a post hole digger or something. So there's a turning block mechanism, and we already designed a double slider mechanism for the same motion, and of course we can easily design 4-bars. Did we design a 4-bar for this?
Yes, we had a double crank, I believe.
Right, we had a double crank 4-bar that we designed to move through these same positions. Even for these 3 positions, notice there are a lot of places where after you carried out the design and you came up with a design that theoretically can be assembled in those different positions, still it won't satisfy the requirements because it may need reassembly in order to move through the positions, or it may need guidance to go through the positions, or it may be a double rocker mechanism and you may be looking for a crank rocker, or for one reason or another the mechanism won't satisfy the particular requirements that you have. One kind of requirement that people often have is good transmission. If a mechanism is going to be transmitting significant forces, you want to have good transmission angles on the mechanism. And so a designer can specify as a requirement that he wants to have the computer show him the transmission angles of the mechanism while he's synthesizing the mechanism. Let me turn off the grid. So you can see these menus perhaps a little clearer without the grid behind it. Now I'm going to pick another option called set signal parameters. What it is a capability which allows us to tell the computer exactly what we're looking for in a mechanism. When do we want it to flash that signal box? Right at the moment we told it, flash the signal box if you've got a mechanism which is either a crank rocker or a double crank mechanism. don't bother telling us by flashing the signal box if it's a double rocker or a non-Grashof double rocker, because at the moment we aren't particularly looking for one of those mechanisms. Also, we told it to flash the signal box if it drives through all the positions, and we could ask it to only flash the signal box if the mechanism meets certain transmission angle requirements. We can specify exactly what kinds of requirements we want it to meet. Now this is sort of like a Michelin guide to restaurants. These numbers represent different levels of goodness or desirability in a mechanism. And we can change these numbers. Why don't you make that a 90? These numbers are different levels that we want the mechanism to satisfy. And what we have said is, if a mechanism has a very bad transmission angle, we'll call it a one-star mechanism. If the transmission angle is better than, say, well, leave that 45 degrees, we'll call that a two-star mechanism. If its overall transmission is better than 45 degrees, and say if it's better than 40 degrees deviation in a design position, we'll call it a two-star mechanism. So let's make that number into a 40. And here we've said if it's better than 30 degrees anywhere in its cycle, we'll call it a three-star mechanism, and a four-star mechanism if it's better than 15 degrees. In the design position, that's kind of a tight requirement. Let's make it 10 degrees, which is an awfully good deviation angle. So in other words, we've specified exactly the kinds of mechanisms we're looking for and what we're going to consider to be a good mechanism that we want called to our attention. Let's turn the grid back on. So now the computer is only going to flash that signal box and call mechanisms to our attention when they meet all of those different design requirements. Let's put up a fourth position.
Now, once again, as we get a greater number of positions that we're requiring this mechanism to move a body through, it's a harder requirement. And so our freedom of choice of where we can put these different kinds of joints is going to be much less. A four-position problem is much harder than a three-position problem. Right now, he's grabbed a moving pivot. The computer is right now calculating the loci of possible locations for that moving pivot that would satisfy these four design requirements. So these are the loci. There are two curves on the screen. One is a curve of possible circle points, or points in the body that lie in a circle in the four positions. The other curve is the locus of possible centers of those circles. So if there's a point of the body which moves in a circle through the four positions, then we can guide that point through the four positions with a single link that pivots around one point of the framework.
This point that I just grabbed is a slider point. That's the only possible point that travels on a straight line as that body moves through those four given positions. With this choice of one link and that slider point, this would be a slider rocker mechanism, and it wouldn't be a good one because it needs guidance to reach positions 2 and 4. I could grab this turning block or pivoted slider, and I'd have a rocker rocking turning block mechanism, which again wouldn't satisfy the design requirements. Now if I grab a second fixed or moving pivot, again the computer is constraining me to move it only along the curves, and it's showing me where the moving pivot must fall in each of the alternate positions, and simultaneously it's telling me exactly what kind of mechanism I'm going to end up with. So you can see as I move my pen crudely around on the screen, the pivot goes to the closest place on the actual locus that is compatible with the motion that I've specified.
These kind of designs are really quite difficult in practice. Simply calculating those loci is a difficult task, but once the loci have been calculated, there may still be no solutions. So the advantage of this type of approach is you can very, very quickly scan along the loci of possible joint locations and find if there are any desirable regions of good solutions. Here we've got one.
Now notice how a very slight distance along the curve and you go from a good design to a terrible design. Now down here in the lower right corner of the screen, for this particular double crank mechanism, which is a one-star mechanism, it's telling me exactly what the transmission angles are for that mechanism. And that particular one has an 80-degree deviation angle, which is really terrible. With a little looking around in a few seconds, we could probably get a very good mechanism, if there is one. And here I've got one with 47 and 40-degree transmission. And look, down here in the lower left, it flashed two eurekas, meaning this meets my second level of requirements.
So let's watch this one go.
Well, let's see if we can optimize it a little bit more by searching on the position of the first link. Now, there are a lot of subjective requirements that a person needs to satisfy in doing a design, as well as simply matching the design positions and being able to assemble the mechanism in the different design positions. And with Kinsyn, this is very easy to do. By hand, this process is virtually impossible because it would take so long to calculate these loci. And usually you want to make some changes in the mechanism or in the proportions, and so it's a very laborious iterative process. So let's analyze this and see how it moves around. Now this linkage moves exactly through the four given design positions. There it is in the second position, the third position, and swings up and into the fourth position.
Miraculously, it managed to turn that body back over again to come around back into the design position.
Let me turn off all of the links of the mechanism and show you just the moving body moving around so you can see how it goes exactly through those design positions. What were you saying, Andy?
Well, I was about to say that to try to come up with locations of pivots to do something like this by hand is just almost an impossible task. It's very, very difficult.
Even working from a computer printout of these design curves, these loci of possible pivots, it's almost impossible to get a good design for a general problem. Just so you can see how the mechanism moves in between those positions, we have a lot of options for displaying the picture in different ways. Let's go back into the synthesis part of the program. Just for curiosity, take a look at these curves and see how they look. Suppose I throw away this fourth position and put up a different fourth position. Let's put another position over there. So we want to guide a body through there, and then flip it over and move it into that position, and just see how dramatically those curves will change for this difference of position. It's very surprising how a slight change in the required performance causes very dramatic changes in the shapes of these curves. In this case, I've got a pretty drastic change of the motion, but sometimes just wiggling one of the angles of a desired design position a very slight amount will cause a great change in the shape of the loci. Here's another double crank that will go through these new four positions. And then there's another branch of the locus down here, and here are some double rocker mechanisms that go through the positions. Let me now throw away that linkage, and let's put that same position that we had before as a fifth design position. See what the possibilities are for these five positions.
5 design positions, that is 5 positions in the plane, are the maximum theoretical number for which we can design a 4-bar linkage mechanism.
For 5 positions, there not very many possible mechanisms. At most, there'll be 4 possible pivot locations for the fixed pivots and for the moving pivots. So you can at most design 6 mechanisms for any given set of positions.
In this example, there happened to be the full maximum of 4 choices of links to guide this body. So what we've had the computer do is to display over here on this screen a little summary of all the possible mechanisms that you can make out of those 4 links. So there are 6 possible 4-bar linkages. You can see out of the 6, there are 2 of them here that say good solution, which drive through all the positions. One of them is a double rocker mechanism, the other is a double crank mechanism. Now that was really pretty fortunate. Very, very often you find no solutions at all for 5 positions. Though if you move a position a slight amount, you may get lucky.
Back here on the screen, as you can see, as I move through these 6 possible solutions, see most of them don't do the job. This one misses positions 2, 3, and 5. Even though it's a theoretical solution to the problem, in the sense that it can be assembled in all 5 positions, it can't actually move through all the positions.
Just to see how the solutions change, why don't we change the motion a little and just recalculate the solution?
Okay, I'm making a slight change in that position, and let's see what happens to the possibilities.
So once again, it's performing this 5-position calculation, and this time it found only 2 links to guide the mechanism, and once again on the screen it summarized the one single solution, which is a double crank mechanism, but it needs reassembly to reach 3 out of the 5 positions.
Now, the computer didn't fail us in this case. This means that there's theoretically no other possibility. In other words, the computer did exactly what it's supposed to do, and it just happens that when I made that slight change in that position, I went from having 4 solutions to no possible solutions. And that was the only possible design for a linkage, and it would not work. So you can see how sensitive these solutions are to very slight changes.
Now once again we've changed back to this other solution. So this is the same one that we were looking at before. We have 2 possible mechanisms, a double rocker and a double crank. Why don't we try changing the motion further?
Well, let's see how this mechanism moves.
Now this is a pretty big one. Maybe we should change the scale.
Shrink the mechanism down a little bit and shrink the motion down a bit.
Unfortunately, for 5 positions like this, we don't have very much choice as to where to put the links. So we really have to take what we get and see if it's any good.
This is the only solution theoretically possible for these 5 positions. It's possible to mathematically show that no other solution actually exists for this problem.
Well, there was
you can see that there was a possibility for a double rocker mechanism, but no double crank mechanisms. Let's turn off the grid and turn off the joint symbols and just show the moving plane moving through the 5 positions.
So what's being animated is this same mechanism, but we've made all the mechanism parts invisible so that we can watch the motion of the body being guided through the 5 positions.
You can see that it does go exactly through the design positions. The chances of finding a design like that by hand are virtually impossible. In order to find a working design, a person would have needed to be able to visualize that for this particular motion, the only possible points in the world that would work were those 2 points in conjunction with these 2 points. Going back to the synthesis part of the program, we have a choice of either closed-form synthesis or an experimental feature that we're still developing, which we call numerical synthesis. We just put up 6 plane positions, which, as everyone knows, is an impossible number for a 4-bar linkage to move through. But we are asking the computer to find a mechanism that will, as closely as possible, move through those 6 plane positions. With the linkage layout part of the program, I made a 4-bar that obviously will not pass through those 6 positions.
Let's distort this and then examine its motion and see how poorly it does and see if we can converge to a solution. I can't imagine that that's going to get those positions too well, the way you just moved it around. So here's what this mechanism does.
This is the starting mechanism. The thing that's unique about this numerical synthesis capability is that it's independent of the topology. We can lay out a 6-bar or an 8-bar mechanism, and we can specify a function or a path or a motion, and the computer will try and meet those requirements as closely as it can by a numerical search procedure. The computer is now shifting around the dimensions of that linkage. Remember, it started way over here, and suddenly a numerical optimization part of the program, which is a least squares pattern search combination using least squares stretch rotation operator technique that we're developing, is shifting these pivots around and trying to get that linkage more nearly to move through those given design positions. You can see it pulled these pivots to over in this region.
So it's trying to meet these requirements as best it can, and I think we were pretty lucky on this one because there's this error over here which simply represents how much the mechanism misses those positions by, and is trying to reduce this number as close to 0 as it can. And for this example, this is really pretty good.
Let's analyze this and see how close it comes to the positions. Now you can see that it does go pretty close.
It's pretty darn good.
To those positions. And for further improvement, as we get to each position, we can put in, using our own intuition, a guess as to what the link rotations should be. You can see every time I come to where I think would be a good guess for that position, I push the button. I just stored a set of guesses that I made as to what the proper link rotations should be. And then we can go back to the numerical search algorithm.
Now we're going back into the search process to see if we can improve upon this solution.
You can see that the computer is still shifting these pivots around. It makes pattern searches and pattern moves, and every now and then you can see these pivots take a giant step, and the error decreases by some dramatic amount.
This part of the program is really still under development, but is capable of handling almost any kind of mechanism topology. As it develops, we think it will be very, very useful in designing many kinds of complicated mechanisms for a variety of different design requirements.
The error is down to 1.5, now 1.4, and you can see that the linkage is quite different from the one we had earlier. If we now go to analysis, we'll see how this new mechanism moves around. If we had 5 minutes or so to wait, we could get the error down probably close to 0.
We certainly would never get it to 0 since it's 6 positions for a 4-bar. It's got the right idea.
If you depend on the computer to search by itself, it's an exhaustive process, and the computer can never get as good an answer as the combination of a human being looking at the display and using his intuition to lay out a fairly reasonable starting guess for a mechanism, and then to pick off good positions for starting guesses. The human being and the computer make the much more effective combination than the computer just by itself. Now there's another capability that we have with this program, and that is we can store away mechanisms for future reference, or we can recall mechanisms that we had designed earlier and stored on the disk. Here's a bivariate, or 2-degree of freedom mechanism, which I had designed a few days ago, and I can change its proportions slightly and then analyze it and show its performance. This particular mechanism is typical of a class of devices which I call precessing mechanisms, because they have a single fixed pivot and they generate motions which are symmetrical about that single fixed pivot. One kind of thing that these are very pretty and useful for is generating symmetrical coupler curves. We can show you the curve that this point of the mechanism traces out. Any points that we want to trace out as coupler curves, we simply touch them with the pen and the computer will show us exactly the motion that that point traces out. A mechanism like this could be used for doing decorative stitching in a high-speed machine, for instance. Let me make the mechanism itself invisible. Maybe I'll leave the joint symbols on so you'll see them moving around in the dark, and we'll change the gear ratio in the mechanism slightly and show how the coupler curve varies with a slightly different choice of a gear ratio. This is the same linkage, but with different gearing between the two drivers.
This is even the same point of the same linkage. We're watching trace out this path, but with a different gear ratio, we get a completely different path. Let's see if I can come up with an interesting gear ratio here to produce
let's pull out a different mechanism and see.
Okay.
And see if we have another one that would be interesting to look at. Here's one which will give us nearly symmetric curves, but with a slight amount of distortion, which gives them a little bit more artistic interest. Let me pick this point as a coupler point, and that point as a coupler point, and make this mechanism invisible, and we'll see what it does.
So we're tracing two different points of the mechanism to see what kind of paths they trace out.
With a very slight change, I could make this into a symmetric coupler curve tracing mechanism, but as you see, this is giving us a slight amount of asymmetry. The number of peaks and points on this depends on the particular gear ratio we pick.
So,
what were you saying?
I was going to say that after it's completed that curve, since we used a nice integer gear ratio, it would simply continue to retrace that same path over and over again. So what are you going to build now?
Well, I thought we might show the graphics capability. Because of limited amounts of time, we've been only showing how you can design and synthesize linkages to produce motions and how skeleton linkages move around. Now, at the start of the movie, we showed you an actual mechanism with a moving linkage and a body fastened to it, all moving around. During the synthesis and the draw mech part and the analysis part, we can actually draw in blueprints of machine parts and show how they would actually move when driven by our linkage. And this is the graphics part of the program, which allows us to draw in those blueprints. It's a very powerful graphics capability. Let me create a random machine part. Suppose we want to have an ellipse over here. And we'll put the two ends of the axis there, and we can stretch it out. Whoops, I lost it. Let me throw an ellipse down here. This part of the program is a very flexible graphic input program which allows us to draw in parts, draw in circles, erase points, lines, connected figures, scale things, make them larger, smaller, shift them to the right, to the left, down, up. Move figures around. Scale objects. Flip them inside out, backwards, forwards.
We can also create different sub-pictures, and we can split a picture into sub-pictures and manipulate each sub-picture individually, doing different kinds of scalings or rotations or combining sub-pictures or whatever we like. It's really a very powerful general graphic input capability. So what are we doing here? We're rotating around a point. A circle, and the center of the circle is equidistant between 2 points, and there's one of them, and there's the other, and here's our circle, which we can make any size. And there are all sorts of things built into the program, like gravity to the various points, so you can put points exactly on points. Here are some of those types of options which we can turn on and off individually.
Point gravity means that the pen will jump to a point. Line gravity means it will jump to the nearest line. Grid gravity allows us to draft things very quickly because the pen jumps to grid coordinates. We can turn these things on and off. We can make it automatically round to the nearest 15 degrees on angles. We can put it into a sketch mode, which allows us to sketch in any sort of a figure that we'd like. Let me erase the old figure, and
I think I know what's coming already.
sketch in any sort of a machine part, or we can go back to the drafting
or other
mode,
kind of picture.
or other kind of picture. And then we could take that picture and we could scale it down, the entire picture, or we could scale any part that we could draw a box around. And then we can return to the main part of Kinsyn, which allows us to synthesize a mechanism. And we can design a linkage. Let's design a 6-bar. While we're synthesizing a mechanism, we can have the actual frame and the body in the background. Again, as you can obviously tell, this is totally unrehearsed, and we haven't pre-arranged these examples, but these things we're doing on the fly, and you can very easily design a new kind of a mechanism. Which the computer hasn't seen before. In this case, it certainly hasn't. We can go to the analysis part of the program. And we can hook our picture onto the mechanism. So there we'll take that picture and we'll fasten it onto the mechanism, and we'll see how the mechanism moves that picture around. Let me turn off the grid, and let me make the linkage invisible. And let me make the joints
Joint
of the linkage invisible. And now we can see how that picture moves when driven around by that linkage that I just designed.